Okay, I'm going to start 8.5 here with a problem that we've been doing. The problem looks like this. So AT is parallel to BN, which means you have some similar triangles there. FA is 12, FT is 15, AB is 8, and let's find TN. Let's call it X. So in what we know up till now, you would do it like this. You would do 12 is to 20, so 12 is to the entire length, as 15 is to 15 plus x, and then you would solve for x. X will end up being equal to 10, okay, if you solve that. What I'm going to propose here is that you can actually do this is to this as this is to this and get the exact same answer. It'd be 12 is to 8 as 15 is to x, like that. Okay, and hopefully you can see that this is going to be 120 is equal to 12x, so x is equal to 10. Let's see why that works. That, by the way, is called side splitter. So using the diagram above, you're given that the triangles are congruent, are similar. So triangle, and I'm just using this diagram from up here. Okay, so I'm saying that triangle FAT is similar to triangle FBN. And what I'm trying to prove is what I said. I said that I'm trying to prove that FA is to FT as AB is to TN. Or no, sorry. FT is to TN and FA is to AB. Sorry about that. Let's get the letters in the right order there. So, what I want to show you is that, okay, we know that FA is to FA plus AB as FT is to FT plus TN. That's what we used to solve the problem the first time. And so if I cross multiply, I'm going to get FA times FT plus TN is equal to FT times FA plus AB. Distributive property. So I get FA times FT plus FA times TN equals FT times FA, notice this is the same, plus FT times AB. Subtract this from both sides, you get FA times TN is equal to FT times AB. And hopefully you can all see that those are the same. Notice if I cross multiply here, I get this, and if I cross multiply here, I get that. So basically, side splitter basically says that if you have a line that's parallel to one side of a triangle, and intersects the other two lines, or the other two sides of the triangle, then it divides the sides proportionally. Okay, so I mean it's simpler than it sounds. So basically it would be, in this particular case, it would be this is to this as this is to that. So it would be x plus 3 is to 2x as 3x minus 6 is to 2x plus 7. Side splitter. If I wanted to solve this thing, cross multiply, it's going to be some ugly stuff there. I think you get, you're going to end up with x equaling 7 or negative 3/4. And this is going to end up being, for those of you who are interested, but it's going to end up being 24. Okay, so that's side splitter. Let's jump to the next page. Okay, moving on to page 2. This is the second of the 3 theorems that I want to show you here for this section. This one's called the angle bisector theorem. Okay, and it's a little easier just to, I think, show you than to write out what it is. So basically, if you have an angle bisector here and here for this triangle, what it does is it'll split it so that this side, let's call it A, B, C, D. So it'll be A is to B as D is to C. Or I can do A is to D, so this is to this, as B is to C. And hopefully you can see that these are the same, right? All I did was I basically switched these two guys and I got these. Okay, so that's the pattern. So whenever you have a triangle and you have an angle one of the angles bisected, that's what you can use as far as setting up a proportion. So let's try this one. Sides of the triangle are 15, 20, and 28. So 15, 20, 28. How long are the segments into which the bisector of the largest angle, this one up top will be the largest because it's opposite the longest side. So it's going to be an angle bisector here. And you try to figure out what these segments are going to be here. So this is x, and let's call this 28 minus x. And so the proportion I'm going to write is 20 is to x as 15 is to 28 minus x. Then I cross multiply and solve. X is going to be equal to 16. And so the other one's going to be 12. Okay? And then the last theorem down at the bottom here is called an unnamed theorem just because it doesn't really have a name. And so again, basically what happens here, it's just easier if I just show you. But basically, if you have a set of parallel lines and you have some transversals, these are transversals, these pieces of the transversals are going to be proportional. So if this is 3, this is 8, this is 9, then I can make this x. And what I can do is I can do 3 is to x as, well, something is to 9, and it's going to be the entire length of this side. So it's going to be 11 is to 9. And basically, the way this sets up is I could do 3 is to x as 8 is to, well, this would be 9 minus x. So I could have also done 3 is to x as x is to 9 minus x. Or I can do 3 is to 8 as x is to 9 minus x, like that. What I can't do, the only thing you have to be careful of, is I can't say like 3 is to this as 8 is to that. So I can't do like 3 is to 9 minus x as to 8 is to x, something like that. That does not work. Okay, hopefully that makes some sense. The unnamed theorem is just kind of recognizing that the parallel lines are going to divide these transversals proportionally. You got the angle bisector theorem, which, by the way, just want to let you know that the angle bisector theorem will show up again throughout the rest of the semester. So whenever you see an angle bisector, put a star next to this, asterisk next to that. The problem might have something to do, and it likely has something to do with the angle bisector theorem. And of course, on the front side with side splitter. Okay, I'm going to let you try some problems on your own now.